Welcome, folks. Welcome. I think it's a vote of confidence to be seeing you back here. Welcome to the new ones. We've been dealing with PLC programming. We are looking at the Delta PLC, and we are doing logic gates. We are looking, I think this is either the final or the second final. I'm not sure how long this is going to be. If it's long, I'll make it 2 sessions. But if I think we've taken, we haven't taken too much time, I'll probably put the 2 sessions together. I want to do the exclusive OR and the exclusive NO. Let me rather do the exclusive NO now and make the video nice and short, and then I'll do the exclusive NO later. Alright, so exclusive OR it is. Let's go and get our software, which is the WPLSoft for the Delta PLC. Where we have our PLC is the DBP PS02, and there is our programming platform. And then we come there, we say new, we can hit Control and plus N. You see, it will give us that. Now we can say that dialog box there, we can say what is our new program title going to be. Is still the logic gates, and then we are looking at, we said we are using the Delta PLC, and then to do the exclusive OR gate, the exclusive OR gate. So it is an OR gate, except it will not accept a non-OR state. All right, unlike the exclusive OR, which actually included which actually responded to an end state, this gate will only respond to an exclusive OR scenario. All right, it will be very strict on the definition of OR. Let's maximize this so we can have a good big picture there. Let's go on and say, remember the inclusive OR. What I call the inclusive OR is one of them, I will not name them, and the other in parallel. So we've got 2 normally open inputs in parallel. We could have more, could have 3 inputs if we felt like. It could be, only thing is probably they'll be named different. They can't have the same name, otherwise it's just a buffer. It's just the equivalent of a buffer. Okay, let's first accept that. Then this is X2. If it's 3 inputs, we could go on to 4 inputs. As long as they're all parallel, it will just depend on the number of inputs we want. So as long as it's parallel, it is the inclusive OR. Right, now what is an inclusive? Let's look at our OR gate. All right, our OR gate is given by, I want the pen, I forgot where my pen was. Our OR gate is given by, let's say, that's why I prefer to call it AB, because I want our OR gate to have been our output. Let me remove this. Okay, our output there will be given by, if I use XO, what looks like a plus is an O symbol, X1 or X2, it is our output. All right, so our output is given by that. Now it is what looks like a summing scenario. Now our output will therefore be, our F2 will have to be, or in this case, because I've used X's, let me rather use a Y, because I've used the X's there. I did not use A's and B's. So let's rather say, if this was our output, we can come here and say click. We have to select a tool, we have to come in F7, and you say Y0. All right, so now this here is what an inclusive OR, we explained this before with 3 inputs. So this is what we call an inclusive OR gate. Now when we want an exclusive OR, now what it means is we have, let's look at, we know that the AND gate, let's put an AND gate, we know that the AND gate would be, oh yeah, all right, let's have another input there and call it 4 or 3. I'll just do 2 input. or maybe do 3 input just for thing. So where is our other one? We call it x4, and our other one, our last one, if you do 3 input, we could probably call it x5, and there is our output. Let's say our output, that icon, let's say y1. So y1 would be, if you want to look at this one here, our AND gate would be a product, and that would be, let's take our pen, x3 by x4, actually and x5. This is equal to our y1. So what does it mean? It means that the times function is a what? Is an AND gate, and it means that our what? Our plus function is an OR gate. Let's go and look at our exclusive OR gate. Our exclusive OR gate is given by, I'll use A, B's and C's here. Let's say A, B, which is a times function, not for the one, or A, not A, B, not for the other. So this here would be our, let's say this is F, alright. So what it means is that our exclusive OR gate is given by a combination of an AND gate, another AND gate, and the two are actually what? Odd. What does it mean? OR means parallel, AND means series. So I've got a series. So if I come and put this here, if I try to put this on our programming, we'll come there and say we want instead of U, we don't want that. We come here and say we don't want the Y, I want the Y comes down to be removed, the vertical line. I'm clicking. Alright, let me just right click. I thought clicking on it will just ping it. Let's just right click. Now I am deleting the vertical line. I want to put them an AND situation. I want to put an AND situation of a normally open with a normally closed. Remember I said that not from the previous scenario, we said our NOT gate was the normally closed. So this is a NOT B. So what we're going to do is we're going to say a normally closed X1. You're going to say X1 there. Normally closed, but it's X1. What do I have? I have, because it's series, is therefore an AND scenario where the one is normally open and the other one is normally closed, but it's O, meaning a parallel scenario where I have, again I'm going to come here and say, let's delete the vertical line. Okay, now I'm going to close this with what do you see? The variable is the same. It's A. Let me take the pen. The variable is A and A. In the one AND gate, the A is what? Is normally open. In the other one is normally closed. So what it means is that this here is going to be the same variable, which is x0. So this is going to change to x0. I'm double clicking, so x0. Okay, but it's a normally closed version because on the other side the A is not. There's A, the other one is not. There's two AND gates. That one, this first AND gate here, let me take a pen. This first AND gate, another AND gate. So it means I have to have an AND here. The variables are, let me rather do this. Yeah, the variables are the same. So this is going to be x1 as well. It's A and B. So it's x1 as well. So we are going to say x1. Oh, what did I do? The instruction x1. And then what do we have now? We in the first instance it was not. So not, remember, is a what? Is normally closed. Here it is open. All right. So we have x1, the same variable. If you allow A to be x0, That means this here is what? Is A. But there A is not, so this will be not A, so it's not x0. Right? If you let B be x1, here x is not B, which is not x1, which is not is closed, and then the other one is B on the other end is B, but together they are also together they are parallel. I think this makes the understanding a little bit better. Let's go and delete. We don't need this. Delete the row and delete that row as well. What we now have is we have combined. Here what I did was I've used our understanding that the what is a knot is a normally what? Is a normally closed. We've used our understanding that a series means end. So that line there, let me take my pen. That line there is literally x0 and x1, except it's a closed, so therefore it's not. And that line there is x0 and x1, except this is closed, so it's a not. Alright, so as you can see, but because together, so the one line is x0, x1, not. The other line is x0, x1, but the not is on x0 this time. So, but together they are parallel, so parallel is a means OR. Alright, so this is literally how easy the exclusive OR is determined. Now let's see if this works. Remember, exclusive OR, if we have an input x0 and x1, they could both be off. This one could be off, the other one on. The first one could be on, the second one off. They could both be on. Remember, with this is our what? Our output y0. This could be A, B, and C, or any other letters, right? This could be A, B, and F, for instance. This could be F, A, B, and F. Okay, this could be A, B, and so it could be anything. It could be anything. It could be anything that you, any letters, any combination of letters that you prefer. All right, it's not really an issue. Now we remember that with the exclusive O, with the inclusive O, sorry, this was off, but the rest was high. Okay, because if any of them was on, you had to have an output, including the non-O state. Okay, which was the what? Which is the end state. That's why, hence the name, hence the part of the name that says inclusive. That inclusive is derived from the inclusion of a non-O state, which is an end state. Now let's go on and say, I'm going to remove this so that it's clear. I'm removing it from our program, not from your brain. So I hope it still stays in your brain. That part we don't need. What I'm then going to do is I'm going to say, let's observe and see if this is now exclusive also. We are going to come and say, let's simulate. Then we're going to say, okay, let's bug and run it and see if it works fine. If I run it, you can see normally closed again reminds you that without doing anything on its normal state, that one is ready to pass power through. Now we come and say, let's activate. Let's start with the first scenario there. As you can see, we have no output pause. Now let's confirm this by getting out of debug, sorry, and then let's run. It's on stop mode. When you run it, it starts on stop mode. No, sorry, we'll put it online first. We'll put it on online. Now we are running it. Yes, we wish to continue. Now you can see, yes, this output is confirmed off. When the two of them are not activated, yes, it's off. You can go and verify that that is the case. Come here, make sure it's set off, because we want to make sure we have done nothing. So meaning that they are both off. Okay, so as you can see, there is no output, so this is confirmed. All right, the first state is confirmed. We go and try and check the second state. The second state is us now coming in what? Activating X1. So we come to X1 and say, all right, we are going to change you and set you on. Now as you can see, it might have broken here, but because X1 was open there, it closed there. As you can see, our power is going through. So yes, this is confirmed. So we are still on O. Now we come and say, okay, what about this state here? Meaning that you set them off again. You set them off again, and they are back to the normal state. Then you set that one on, set it on. As you can see, that was normally closed, so it broke. That was normally open, so it closed when you set it on. So that line is confirming that output is high as well. You can see our output is high then. However, we know now that we've set this one on. So we are going to come and say, okay, set both of them on. So this is on. Set on, just to confirm, that is on, set off, set on. As you can see, this was normally closed, so on the off condition, this would have been high and that would have been low. But because now you set it on, it broke the normally closed and closed the normally open. Same here, when you activated this, what was normally closed broke, and what was normally open closed. What do you see? We don't have power, so it says nope. I am rejecting this state. I am not taking the end state. I am only allowing the O state. As you can see, this is U, O, U, and we've got our power, but it doesn't. It rejects now the what? The end state. So this here is our exclusive O state, because we only get our output when the inputs are in an exclusively O combination. All right, this one active or the other active, and you get a what? And you get an output. All right. Thank you so much. I hope this was fun. If you did like it, prove it by hitting the like button there, and also remember to tell us where you are on the comment section. Give us suggestions for improvement, and hopefully you are part of the family. If not, hit the subscribe button there, and then let's grow our numbers. We have one last gate left, and we'll see this gate in our next session. Hope you had fun as I did. Thank you.